with the most pretentious title ever. Anyway, I would like to thank the organizers of the conference, in particular Professor Tannenblatt. It's been wonderful. And since it's the last talk, let me just ask everyone to give her a big round of applause, because it's been a great conference. Thank you very much for... No, I'm just kidding. All right, so the idea here is I'm going to try to justify the pretentious title. And the setting will be, I'm going to pose a very general problem involving black holes and the universe, if you want. Then I'll make a standard simplification, and then even make a even stricter simplification to which I can say something about this title. So let's see what's the general framework, okay? So just to keep things simple, imagine this is space-time. Time flows that way, and this is some slice of space-time. Now space-time is some Lorentzian manifold with some Lorentzian manifold L with a metric G bar. I won't throw in dimensions at this time because eventually we'll want to have it in arbitrary dimensions, so let's just leave it like this. And then when you have one of these Lorentzian spacetimes, there's something you can talk about, which I'll put it as a little ideal place there, a little cloud called null infinity. So there's this, let's just to keep the drawing simple, let's just say there's this thing called null infinity. And then, so in this spacetime, some points that lay in the spacetime have, if there are certain curves that can reach this null infinity. These curves are, let's say, geodesics that are null geodesics. And some points in the spacetime, if you look at all the set of all null geodesics emanating from those points, they can never reach this null infinity. So there's two types of points. Those that can reach null infinity via null geodesics and those that can't. So this defines a region in your spacetime where, let's say, the guys inside this region cannot reach null infinity. And this thing is called the black hole region. All right, so when you have a spacetime, you can define this. I'm going to be kind of sloppy here in the definitions. So just to give you some kind of an idea. All right, and now there's a special part of this black hole region, which is its boundary, this blue thing. All right, and then this is called the event horizon. The idea is that once you cross this boundary, you're walked into the wrong part of space-time. You'll never be able to reach null infinity from there, also known as you're sort of sucked into the black hole. This is the story. All right, so how can you try to study this problem? Well, I put there a slice for a reason. The idea is to sort of, okay, we take a picture of the space-time as we see it today would correspond to looking at the fixed time, so we have a slice. And the question is to examine this slice and see what you can say about it. This is the general idea. But the problem is that this is a highly global question, namely, you need to know the whole space-time to see whether you will ever be able to reach null infinity. You see, you may be standing here or here, and you think you will never be able to reach null infinity, but maybe later on you will be able to reach it. So in order to properly study this problem, you should first solve the full evolution equations for the Einstein equations, and then you can talk about it. But naturally, we don't know how to do that. So, well, what do we do? I mean, we don't know how to solve the Einstein equations full in time. We don't really understand these things yet. So, let me just try to say what we can say. So the idea is the following. We take a space-like slice. So we're going to think of this guy here is going to be some mgk. So keep in mind you have a slice of space-time. This is a triple mgk, where m is a hypersurface. Furthermore, we require it to be space-like. What does that mean? It means that G, which is the restriction of G bar to M, is Riemannian. So the Lorentzian metric, when you restrict it to this hypersurface, will require it to be Riemannian. So other way of putting it is that you have a sign condition for the tangent vectors at every point. And K is, let's say, second fundamental form of the slice, or if you like to call it extrinsic curvature, whichever way you would. So this is what you would initially talk to about initial data. So our initial data would be sort of this slice, and see what we can say about black holes and stuff like that. So what's a general problem? The problem is to say something about black holes and whatnot. But I guess I should have said that what's a big issue about this is that the horizon intersection the slice. This is very hard to determine. Let's say at this point impossible, because need the full evolution. So you would need to be able to solve for all time the Einstein equations forward with this initial data to be able to determine what that thing is. So that's a big issue that arises. And so, let's just start imposing some conditions. Maybe we can get away with something. All right. So first of all, I'll talk about some physical assumptions. So this will help. These assumptions will help us sort of pin down the problem. First of all, we're going to talk about isolated gravitational systems. So what does this mean? So we want to study what does relativity have to say about a system which is isolated in the sense that it's, say, a star or a black hole. It's not like they're not going off to infinity. It's not infinitely many black holes shooting off. It's just sort of some region where the action is happening and there's nothing else outside. So if you translate this into math, this means that the metric is asymptotically flat. So you can think of, if you like, metric is, I'll be more precise in a little bit, but the idea is that the metric sort of becomes very close to the metric, to the Euclidean metric outside a compact set. And then the other assumption is what's called the dominant energy condition, or DEC. This one says the following: if you, in physical terms, non-negative energy density everywhere in space-time as measured by observers moving in all future pointing time-like directions. All right, so this is what it means in physical terms, but this actually is more precise. So if you call the point-wise energy density, call this thing mu, and the definition is the following: 1 over 16 pi times r minus sum over ij of h, ij, h, ij, plus sum over I of h, I squared. And this is R here is a scalar curvature of G. So G, remember G is our space like slice. Okay. All right, and then you call the current vector density. Let's call this as a vector Ji 1 over 8 pi sum over j nabla j hij minus sum over k hk k gij. Then the dominant energy condition is just the inequality mu greater or equal than absolute value of j. All right. So these are our two main hypotheses. We have an asymptotically flat metric and mu is greater or equal than j, where these are the guys defined related to the initial data. All right. Right. So when you have an mjk like that, you can define some interesting quantities. So for mjk like this, you can define the following interesting quantities, very well known to most of you here, maybe. The ADM mass. All right. It's just global quantity. And it's defined as follows. M equals 1 over 2 n minus 1 omega n minus 1 limit as r goes to infinity integral over SR of sum over ij of dj gij minus di jj mu j d sigma r. So there's this integral which looks like a divergence, and if it happens at infinity, it's called the ADM mass. It's well known. Bartnik and Crucial independently they proved, I think in '84, that this quantity does not depend on the choice of coordinates. It's a quantity defined in terms of asymptotically flat coordinates, but it doesn't depend on them. So when you have a manifold like this, asymptotically flat, you can define this quantity called the ADM mass. So when I said how black holes contribute to the mass of the universe, by mass I meant the ADM mass. So now you know one word in the title. It's a nice drawing, but what the hell. It's not. All right. And there's another notion. Oops, okay, erase the drawing, but let me just recall here. You have your slice, and here you had, let's say, the intersection of the black hole region. This blue guy was the apparent horizon intersect that slice. The apparent horizon you really can't determine by just looking at the slice. You would have to solve the Einstein equations. You don't know what that is. But there is something else you can do. There's some other guy inside here. Or let's say there may be another guy here, which we're going to be calling sigma. This one has a special name, apparent horizon. So we have the mass. Now we have an apparent horizon. So this apparent horizon is a hypersurface in M. So it's not exactly the horizon. If there is an apparent horizon, this guy is going to lay inside the horizon. This is a theorem by Penrose. So it's the best we can do, put it this way, so far. This is defined as a hypersurface for which the following holds. The trace over this guy of the second fundamental K form equals the mean curvature. This is the equation, the apparent horizon equation. Okay, so it's that equation. And so now the title becomes, okay, we have an apparent horizon, so we have some hypersurface, we have the ADM mass, so what's the relationship between, let's say, M and the area of this guy? So this is what we're going to be talking about next. So that's sort of the end of the introduction. All right. So, well, what is it? First of all, let me mention that there's one very famous theorem. It's called the positive mass theorem. Okay, which is so it's Shane Yao 79, then Wheaton in 81. It says the following. So in this general setting, as it is, okay, this non-negative energy density not necessarily with a horizon. So you don't assume that there is a horizon. Then m is greater than 0. Okay. So this is the first type of theorem in those sorts. So it's a big theorem, and it's hard to prove. Okay, it's not easy. I'm going to be more specific about the actual statement in a second when we reduce it to an important special case. So, but in this general setting, this is what's known, and there's some dimensional issues which I'll address in a second. And then there's the famous Penrose conjecture, which is what I'll be talking about. Penrose conjecture says, well, this dominant energy condition plus an apparent horizon of area A, then the mass is greater or equal than a half square root of A over 4 pi. All right. So this is the conjectural relationship between the mass of the universe and the area of the apparent horizon. All this. So I guess that's how they contribute conjecturally. So this is open. Okay, this is an open problem in this generality. There are some things, but in this generality it's an open problem, even in 3 plus 1 dimensions. Actually, Penrose apparently was trying to think of an argument to prove something that has to do with the full evolution of the Einstein equations. Is a very famous conjecture called the cosmic censorship conjecture, and he somehow thought that if this inequality is violated, there will be strong evidence for the cosmic censorship conjecture. I'll just leave it like that. So he proposed it as a conjecture. See, at least it means if it's true, then there's no clear way to violate cosmic censorship. I won't talk too much about that. I don't have time. All right. So let's make. So far everything's quite general. Let's make a simplification. So let's think about an important special case. So important because, well, it's easier, and historically also has been the way, say, Shane and Yao went. So anyway, so this case is when the slice MJK is totally geodesic. So, well, this means that K is exactly 0. Okay. So notice that I have it here. Look at the dominant energy condition, right? So if you throw away H, K. Oh, shoot. Okay. So I messed up my. But these look like K's, right? Good. All right. They're all K's, right? Okay. All right. Yeah. So if you put K equals 0, you erase this term, you erase that term, you erase that and that. So J is 0. All that's left is our friend scalar curvature. So dominant energy condition plus this immediately implies R greater or equal than 0. Okay? So basically now we're talking, so K is vanished, and now we're in the more familiar realm, for some of us at least, of Mg being an asymptotically flat manifold with non-negative scalar curvature. So this is a whole industry, let's say. That's how you get there. All right, so let me present you two seemingly lame examples. So what's the easiest example of an asymptotically flat manifold with non-negative scalar curvature? Everybody knows. Rn delta. Flat space, Euclidean space. And another very interesting example, now this one will have boundary. It's what's the so-called Riemann-Schwarzschild manifold. So what is this guy? Well, you can actually see this as a paraboloid of revolution inside of Rn plus 1. And therefore, I'll make a drawing of something like that. It's actually, it's this flipped this neck here, okay? So it's a copy of this through this neck. But the more interesting way of describing this guy for the talk is the following. You think of it as, say, Rn minus some ball of radius r that you can specify. I don't want to waste too much time there. Times the following with the following metric: u to the 4 over n minus 2 delta ij. So it's a conformally flat metric. It's a metric that's a product positive function times delta, where u is the function 1 plus m over 2 times r to the 2 minus n. R is the radial distance to the origin. So this is happens to be harmonic. This is this fundamental solution for the Laplacian. It's harmonic outside the origin. So Laplace u equals 0. This actually is the same as asking the metric, let's call this guy G. G have being scalar flat for conformally flat metrics. So this is an example of an asymptotically flat plus r greater than 0. Actually, both of these have r equals 0. They both have r equals 0, and they're both asymptotically flat. And now let me just say that this one, when k equals 0, important, k equals 0, let's look at what is an apparent horizon now. Go back to an apparent horizon. Apparent horizon is a hypersurface, so that this equals that. Hey, but this is 0 now. So you're talking about minimal surfaces now. Okay, so minimal surfaces in asymptotically flat manifolds of non-negative scalar curvature are the apparent horizons in this setting. And it turns out that this Schwarzschild guy has actually a totally geodesic sphere in this point. Actually, there's an isometry which flips this thing and fixes the metric. So that's very important. And so let's just write the interesting theorems. So let me just restate the positive mass theorem. It says that if you have mg with r greater equal, so mg asymptotically flat, r greater equal than 0, then m greater equal to 0, and here's an important case, equality. I don't know if can you see this color back there? Can you see this red? Okay. Equality, if and only if, let's say 1. So 1 meaning, well, I put like 21s, but this one. All right. Rn is the only scalar asymptotically flat manifold with non-negative scalar curvature with 0 mass. It's the only one. Now there's another theorem called the Riemannian-Penrose inequality, which is in the likes of that inequality there, Penrose conjecture. Same setting, okay? It says now that mass, I'll write it in the n-dimensional version, is greater equal than 1/2 times the area. So wait, I should say Sigma is a minimal surface, compact surface, hypersurface. There's one more thing here, plus, it's important, outermost. Or if you like, outer minimizing. I'll say a little bit about that later. Then the mass is greater or equal than the area over omega n minus 1 to the n minus 2 over n minus 1. So you have this one and that, and then again, equality. If and only if 2. Okay, so we already saw a few talks, including Professor Fernando Marquez's talk, where he presented some rigidity results. So these are examples of rigid inequalities. You can exactly characterize when equality is achieved. All right, so let me just say something about that. So will it be fair to say that I have until noon to talk, 10 minutes? I hope. Is that all right? It was the official ending time, right? So I started a tad early, but I'll just, otherwise I'll just say nothing. All right. Okay, so, well, I won't write it down then. The positive mass theorem, well, maybe it is worth writing. Yeah, okay, so positive mass theorem, what are the limitations of these things? Is known up to dimension n less or equal than 7, or m is additionally spin. So this is Shen Yao, and this is Witten's proof. So the positive mass theorem is not known to hold in dimensions greater than 7 when the manifold is not spin. The Riemannian Penrose inequality, it's known again up to dimension less or equal than 7. This is Bray-Lee, and then, well, I already put the names up there. And then also, well, there's Huisken-Ilmanen. So they also worked in, I mean, Huisken-Ilmanen and Bray came with 2 proofs for n equals 3 first. Huisken-Ilmanen's proof and Bray's are disjoint. And this one is a little bit more limited. And Bray then and Lee generalized this up to dimension 7. These 2 use the positive mass theorem. And geometric measure theory, which kind of this one also does GMT. So basically, because of this, this number is pretty bad. Okay, it seems that at least there's no clear way to going past that number because of geometric measure theory. The methods there break down. Basically, when you minimize area, you're guaranteed a minimizer which is smooth up to a set of codimension 8. So if you're in dimension 8, you can have a singularity, and then the whole theory goes away, and then you have to. I don't want to get into the details, but I mean it gets tricky. All right, so let me just make a. So I'm gonna the problem. So I want to present somehow a simplified approach to these things for a special case. And that's the case of conformally flat manifolds. Okay, so I'll say in a second what are these. So the question is that here the fact, if you on top of that impose conformally flat, okay, PMT, positive mass theorem, check. You can prove it using the divergence theorem. It's a piece of cake. There's nothing to it. And so the natural thing to say, okay, you can prove the positive mass theorem, piece of cake. What about the Riemannian Penrose inequality? Can you prove that too, piece of cake? So that's so there's a theorem. But Bray and Iga from O2. So this is post Riemannian Penrose inequality of Bray. It says the following: if M3 is conformally flat, then M, and same setting as the Riemannian Penrose inequality, M is greater than some constant times square root of area with C some universal constant. So C positive universal constant. So the thing is that the proof proved using only, say, classical So the challenge here is that go to a conformally flat world where things should be simpler and use simpler methods to see what you can do. So what Bray and Iga proved is an inequality of reminiscent to the Penrose inequality, but they don't get the constants necessarily right, nor the rigidity. All right. Finally, maybe I'll state the results of my joint work with Alex Freire, and then if there's time I'll talk more about the conformally flat manifolds. What are they and what not? So here's the first theorem. So it's Alex Freire and myself. This I have the liberty of calling. This actually, well anyway, it's right. Called volumetric Penrose inequality. Let's call it like that. You'll see why in a second. It's as the following. Suppose mg on top of everything else is conformally flat. Then the mass is greater or equal than twice. And I'll have to explain what this is. To the n minus 2 over n. So equality if and only if 2. So we can prove an inequality like this, which is similar to the Penrose, but now you have a volume. And the volume of what? Well, conformally flat manifold is a manifold which is Rn. Remove a set omega. So look, a set omega here. And then put a conformally flat metric on the complement of omega. So this omega has some volume. And then that volume plays a role in this inequality. Now let me just add here that we need omega to be mean convex. And also you need the mean curvature with respect to metric g of sigma. The boundary of omega, of course, is sigma. Sigma is 0. So you have this sort of this minimal surface, and then you get this inequality. Equality if and only if you're in the Riemannian Schwartz manifold. And so I'll just lay down I'll lay out all the theorems that we can prove, and then maybe we'll see what happens. Theorem 2. This is some mass capacity estimate. I'll say some words about this, again by Freire and I. So we put this in the archive like 2 weeks ago. The mass is greater or equal than the capacity of sigma. And then again, equality if and only if 2. And then we get some nice, as a byproduct of the proofs, we have two other results for Euclidean space. So theorem 3, which we can call Szego style inequality, is the following: 1 over n minus 1 omega n minus 1 the integral of h. So now we have omega subset of Rn mean convex. That's all we need for this one. Not even connected, just mean convex, meaning that the boundary has positive mean curvature. This is that, and then we have a Alexandrov Fenchel inequality, which says that if you add sigma outer minimizing, then you get the following estimate. That. So this, in the last few seconds, let me just say some words about this. First of all, the proof of these things has some classical analysis and some inverse mean curvature flow techniques in all dimensions. And let me just say that the mass capacity inequality was known it was proved in dimension 3 by Hugh Bray, and he used this to prove the Penrose inequality. And actually, this is the only part in his proof of the Penrose inequality where the positive mass theorem comes into play. And we don't do that here. So this sort of gives evidence towards the fact that the Riemannian Penrose inequality should be true in the conformally flat case, because it's not needed, the positive mass theorem. And the last thing I want to say is about this inequality. This was known to be true so the classic Alexander-Fenchel inequality requires omega to be convex. Then Guan and Lee generalized this to mean convex and star-shaped. And so now we just remove the star-shaped and put outer minimizing. So star-shaped is a strong topological abstraction. This allows for many components, and mean convex is just whatever you like. And also outer minimizing is just a very simple condition it's not an issue. It's not a really big abstraction. So I think I don't have any more time, so thank you very much.